The language of numbers is having a greater and greater impact on the world around us. We communicate with numbers, but they also tell stories about how our minds work, our capacity to understand nature, our history and our future. Numbers allow scientists to develop ideas about the world that would be indescribable in words. But are numbers concepts we've invented, or are they discoveries that exist independently of us, a natural language of the universe? The dream of numbers is the dream of making sense. We calculate our lives, each step, how old, how much, how far, what's real, what's best. Give and take to balance the books. Where does proof lie? What happens when money talks? Keep in step, in time, keep counting. Fix a point, draw a line from an A to a B. And go home on the right bus, at the right hour, to the right front door. Keep score.
Mathematics? No, didn't like mathematics. No.
Horrible. I just enjoyed it. A bit of a bore, that's all I could say. I suppose it's my fault, really, because I couldn't get in.
And patients would come into the clinic and with various different problems. And one of the problems, quite serious problems that they would come in with, was problems with numbers. And that could be very disabling. They would be unable to shop, at least be able to calculate change or calculate prices well. Often they wouldn't be able to remember their addresses or telephone numbers, and sometimes not even be able to recognize the numbers on buses. So it was a very disabling situation for them.
Craig Ward is one of the patients working with Brian Butterworth at the Mathematical Cognitive Research Group. Although he's a qualified psychologist, numbers are a foreign language to him. He can't work out whether one number is bigger or smaller than another, and he's incapable of even the most basic kinds of calculation. It means his daily life is full of terrifying obstacles.
When I go shopping, it's almost like a nightmare because you have, first of all, the money with you, which I'm not too familiar with still. Then you have all these prices as you wander around. Everything has a price to it, and I've got to work out, well, how much is this in relationship to something else? For instance, looking at the prices here, what I've got to do is work out what the 2, the 6 and the 5 actually means to me. and then I realise, well, the 2 means something, the 6 means something, and the 5 means something. Then I have to sort of think, well, is that £2 or, and then there's this dot here, then I've got to work out what they really mean. I have great problems thinking about a series of numbers, so as you say, the number line is not something which comes readily to me. Each number is an individual number, and I have to work out every single number as I go along. There's no flow or pattern to them.
Well, we think that there's a special area of the brain that deals with numbers. All the cases of patients with real numerical difficulties have damage to an area of the brain known as the parietal lobe. In particular, the parietal lobe in the left side of the brain. The parietal lobe on the other side of the brain seems to do something quite different. And this part of the brain is quite separate from the parts of the brain that deal with language, which are down here and over here. And also the parts of the brain that we now think have got to do with reasoning and inference, and they seem to be in the front of the brain. But perhaps even more surprising than that is that within the part of the brain that deals with numbers, there are specialized parts of the brain that deal with different bits of number processing. So there's a bit that deals with, for example, multiplication tables. There's another bit that deals with specific procedures, like how you carry and borrow. And we found patients who just make mistakes in that one area.
There appears to be some part of the puzzle missing. You're trying to add 2 numbers together, and you know that you can see your friends doing it. And I think, well, why can't I do this? And you sort of feel, well, it's not quite working properly. It's like when you try and start a car. You turn the engine on, and it doesn't quite catch. And you try again, and it's not quite happening.
I think that abilities with numbers are rather like abilities with music, in the sense that between the people who are really terrible and people who are really very good, there's a continuum. And this may have something to do with the way in which they've inherited the particular part of the brain that deals with numbers.
At 5 months, a child cannot speak, but is able to tell the difference between numbers. Is it only a change of shape, or is a child born with a sense of numbers, already adding and subtracting shadows?
Saddex-iyo labaatan, laba-iyo labaatan,
18, 17,
16, 15,
14, 13, 13, 12,
11, 10,
9, 8,
7, 6,
5, 4,
3, 2,
1, 0.
The numbers we use today aren't a Western invention. They come from the East. India played the most crucial role, giving us a number that was to be a cornerstone, 0.
I think the origins of 0 lies both in the philosophical as well as religious aspects of India. I should say that the word 0 in Indian context, the Sanskrit word is sunya. Now the literal meaning of sunya is void, emptiness, and so on. As part of your spiritual practice, one of the first stages in achieving nirvana was to empty your mind of all impression. The symbolic representation of the void was what was called the bindu, or the dot that you probably find sometimes on the foreheads of some of the Indian women, for instance, even today as part of the ornamentation. Then this bindu, the dot, soon became the whole. And the whole was in fact also part of the type of philosophy which believed, for instance, that we all live in a whole. And to an extent, our salvation depends on we moving out of this particular whole.
The symbol for zero can be traced back to these aids to meditation called yantras. Because it's difficult to multiply or divide without zero, its creation made it possible to work with numbers in an entirely new way.
Zero. Shunya.
Ling. Zero. Dim.
0
Sifr.
kosong
Shunya.
It's generally agreed that the number system as we recognize today originated in India. People put it back as early as probably the 2nd or 3rd century BC. Numbers themselves were something which was part of the everyday life and the everyday thinking of most people. They had come across it in their religion. They had come across it in their recreational activity. For instance, some of the problems that we still study today were problems that were known to most of the people. Words were chosen to represent particular numbers with the specific purpose that these particular words in turn could be part of a poem or a verse which would then be easily memorized by people. Therefore, the importance was not just to be able to work out mathematical problems, but to be able to express those problems in a language which was poetic, easily remembered, and so on.
Being supposed the base, the other which is perpendicular to it is called the side in a triangle or quadrangle. The root of the sum of the squares at the base.
These Sanskrit number poems date back to the 11th century, when numeracy in Europe was still in its infancy. In them, we can see the roots of modern mathematics as we know it.
When we talk about our numerals, it starts around India around the 500 AD and is in Europe by 1200 AD. And the number system within 200 years is now replaced all other systems that exist, including the Roman system and so on, to a very large extent.
Taban. Sagal.
Oshem. Shedem.
Cho. Panch.
Pedwar. Tri.
2, 1.
A new kind of number was found in the cracks between ordinary numbers, irrational. Neither whole nor fractions, they fall in between fractions, immeasurable. Infinitely expanding decimals, the higher we try to build them, they topple over out of reach.
It's hard to say when mathematics first seemed beautiful or attractive to me. I certainly was interested in numbers from a very early age and also in geometrical things. But I remember one particular occasion when I'd been, well, it was a rather elementary fact, but that we all know that 2 plus 2 equals 2 times 2. But I think I'd noticed that if you take 1.5 times 3, it's the same as 1.5 plus 3. And so I think I tried to work out some formula for how this worked. I can't remember what age I was then. I found that quite fascinating, absolutely amazing how you could encapsulate this infinity of different possibilities in just one very, very simple, elegant formula.
The thing that makes a mathematical formula beautiful is that it takes something which is enormous and complex and ungraspable and appears to be chaotic and disordered, and finds a way of formulating it in a way that makes it seem graspable and, I suppose, meaningful, that it has an order to it. E equals mc squared is an incredibly beautiful formula for something so profound. I mean, it's amazing that it can be, that such a thing can be stated in such simple terms. I think a lot of artists would see mathematicians as being involved in a creative activity that had great similarities to their own.
Well, there's something certainly in common between mathematicians and artists, and I would say that mathematicians, to be good mathematicians, have to be artists. The trouble is they're not artists, they don't do the kind of art which is immediately accessible to people without knowing something a little bit more of what they're actually doing in some detail, which is often a great frustration, I think, if you're a mathematician, because you may say you just found some result and isn't it beautiful, and you think, that's lovely, you see, and you want to tell somebody. Well, you see, you can't tell most people. It's like being a very avant-garde sort of thing where you might not have a big audience which could appreciate it.
I think that art's real meaning is as a metaphor. It's a metaphoric language. It's a metaphoric view of the world, which seems to be quite similar to what mathematics does. It's a way of describing the world. It doesn't give you a picture of the world, but it gives you a description within the terms of the language.
What mathematics is about is idealizations. You're not talking about marks in the sand, you're talking about certain ideal structures which, if you like, these marks in the sand suggest to you. They aren't it. It's the idealized structures that the mathematics refers to. Now the thing is that it's so often the case in mathematics that although you may say that you're striving for truth, the way to achieve that is to follow the route where beauty resides. I mean, if you have two things and you're not quite sure which is more likely to be true of the two, and then you ask yourself, which would you rather was true? I mean, if this one were true as opposed to that one, would it be more aesthetically pleasing? And that's often a valuable guide in what is really true. So if you like, truth is the ultimate criterion, but beauty is the way you find it. It's not as though what's true, if you like, is an invention. It's not up to us what's true. What is true is out there. The truth is out there, if you like, and one's trying to find it.
If the pin that you drop is as long as your floorboards are wide, the chances of it landing across a crack are 2 divided by pi. A number we have yet to get to the end of. Pi slips through our fingers, but turns up all over and under our feet as a sense of proportion, of natural geometry.
Pi can be written in many ways. All these are symbols for pi. To find the numerical value of this important ratio was one of the great problems of history.
Let me take you to the computer room. Please follow me and watch out.
With his brother Gregory, David Chudnovsky is a leading specialist in the branch of mathematics called number theory. At the centre of their research has been a lifelong quest to discover what pi really means. To help them in their work, they've built one of the most powerful supercomputers in the world in the back room of a tiny New York apartment.
As you know, the first PC was built in a garage.
Right.
We don't have a garage,
No,
so we built it here.
But you know, it's
You know, as I told you, I think before, we are a full-service company, which in my opinion means if you want to do something, you go out and do it. So we went out and did it.
Right. You would be surprised, but building a computer isn't really something so horrendously complicated as people would think it is.
Russian émigrés who fled from persecution to America in the early 1970s, the Chudnovsky brothers have received little in the way of funding or assistance. They have built the computer with their own hands and paid for it themselves.
As a hobby, it's very expensive, and I would say children don't do this at home.
Pi, mathematical. The letter pi denoting the ratio of the circumference of a circle to the diameter. I'll bet I've read that a dozen times before and didn't know what it meant. The ratio of the circumference to the diameter. The value of this pi to 8 decimal places is 3.14159,265. Wow.
Pi swims in the water because if you have equation of hydrodynamics, it immediately appears in Maxwell equation of electricity. So you cannot turn around and not to hit a pi.
Yeah, I mean it's some relatively simple, but almost everywhere carrying some sort of, if you wish, scaling factor. Every time you take an integral over the curvilinear surface or domain, you will always get a pi somewhere in the denominator. It's just there. I mean, it's amazing that this number is so complex. You would expect this actual number being much easier, but it isn't. Some numbers are certainly more equal than others, and pi definitely belongs in this category, at least in broader mathematical or physical contents. It's certainly more interesting, certainly harder to break, and you know, it's about as real as any other mathematical abstraction.
The Chudnovsky brothers have developed a formula which allows them to compute the value of pi to 8 billion digits, an unofficial world record.
So what you're seeing here is simply display of the digits of pi starting from 3.14 up to whatever it is that the file will end at slightly above 8 billion digits of pi. And they're just displayed in order. If you look at it very long, then you can actually think that you will start seeing patterns. It's a famous phenomenon when you see random dots, you start to arrange them in something making sense. It doesn't make any sense.
.1415926535. 3279.
15, digits of pi are one of the most random sequences known to man. It passes all the known statistical tests which would presumably detect the non-uniformity. However, we know that pi is by no means a random number. Right. So we have really this duality, and you know, it's rather frustrating trying to reconstruct sort of the behavior of a number. It's like you have seen a few, you have got a few scales from the tail of the dragon, but dragon is got away.
8214808651328230. It's because pi is a creature that seems to exist independently of us that it's so enticing. The Chudnovskys have spent 25 years trying to discern an order or pattern in its infinitely expanding numerals. Their goal remains elusive, but like explorers on a new continent, their journey is not without unexpected rewards.
You see, I would compare this to somebody performing Bach or Beethoven and Mozart. It is it's both an invention and a discovery. Because I have no doubt that this number lives, breathes, and is out there. But also there is a process of interpretation and discovery, because I'm sort of trying to unlock its secrets. A number like pi have a certain fingerprint to it. and they do sort of contain in them a reflection of the universe.
So you would say, oh gee, if I would know this, it means that I would know everything. Well, it's not true, but it feels so at this moment.
6 6 4 7 0 9 3 8 4 4 6 0 9 5 5 0 5 8 2 2 3 1 7 2 5 8 5 5 3 5. Oh, we've blown it.
Bach played with numbers, hid messages in numerical code, adding meaning to melody. He could not have known that, like a cloud or coastline, his fugues would reveal other mathematical patterns that showed how each part of a work reflected the whole, as if each piece of a puzzle held the complete picture.
We are living in a universe that has a very, very regular underlying pattern. And when we see interesting surface patterns, the kind of things you see every day, like waves on the sea, for example, or the strata in a rock, you're seeing traces on our level of these very deep symmetries of the natural world. Symmetry is a slightly more sophisticated part of mathematics. Numbers is the most obvious, earliest part of mathematics that human beings discovered. But they're all part of the same thing. For example, if you imagine, I don't have one, but suppose I had a starfish, 5-pointed starfish. Now the symmetries of that starfish would be that when you rotate the starfish to different positions, it looks the same. The numbers are in there as well, 1, 2, 3, 4, 5, five-fold symmetry. So in the description of nature, numbers creep in. And if you're going to model the way natural symmetries work, ultimately you reduce it all back to numbers. Some numbers stand out as having an unusual degree of interest, both mathematically in terms of the internal structure of the subject, but also in terms of the things in the natural world that they seem to describe. I seems to be one of these numbers that we would have had to introduce whether we wanted to or not. It's as if the universe uses it, but we didn't notice. And it's taken us a while to catch up with what's in background going on all around us.
I isn't an ordinary number. It stands for the square root of -1 and was first used just to make some equations work. Real numbers could all be expressed on a number line, but on this there was nowhere to put the square roots of negative numbers. To solve this, mathematicians placed I on a new line at a right angle to the number line. This opened up a whole new field of numbers. Each point could be described by a single two-dimensional number called a complex number. I turned out to be not just useful in solving equations, but essential to descriptions of the natural world.
The number I lets physicists and mathematicians express some very deep patterns in extremely simple natural ways, such as the mathematical equations of quantum mechanics. Now that sounds highly esoteric, but you and I are made of quantum mechanics. You know, if you really look deep down inside at what we're made of, we're made of molecules, the molecules are made of atoms, and atoms obey the laws that atoms obey.
I helps us to accurately describe patterns that we see in nature. Because it's a new two-dimensional number, when it's used with very simple mathematical rules, it generates new types of patterns. The most important of these are fractals, the products of equations which by using I create strangely complicated shapes. Repeating infinitely, their intricate growth seems to mirror the natural processes we see around us every day.
Fractals give us a new clue to the kind of processes that must be involved in shaping things like clouds or cliffs or rocks. One of the very common features of a fractal is what's called self-similarity. This means little pieces of it magnified up look like big pieces. If you look at the cliffs here behind me, you see lots of very clear layers of rock which were deposited at the bottom of the ocean when the rock was formed. If you take a small section of that and magnified it up, you wouldn't be able to tell whether it was a little piece of rock magnified or an enormous, huge piece of rock seen from a distance. I think fractals are very important, not because they explain everything, because they don't, but because they open our eyes to a different kind of geometry, a different kind of structure, a different kind of pattern in the natural world, drawn from the natural world. I think numbers have got a long way to go. We're still inventing new kinds of numbers. We haven't finished. The idea that there's 1, 2, 3, 4, 5 and that's it. Every few hundred years people say, sorry, there's a whole new kind of number you should have thought about. Fractals are a tiny, tiny tip of an enormous iceberg of how the universe really works. Not just the sort of simple patterns we used to be able to understand and count, but the much more subtle structures that deep down inside are mathematical, but on the surface are familiar things like cats and dogs and trees and cows and birds and waves and that sort of thing. That's what makes mathematics exciting for me. It's the realization the universe is so much bigger and much cleverer than we are. And it's full of clues, which if we really work at it, we might just occasionally come up with a new idea like fractals and say, wow, beginning to see something here. Finally started to understand something here. That's what it's about.
In 1202, Fibonacci bred a series of numbers like rabbits, each one being the sum of the two before. Not purely decorative, a pattern of natural growth found in the spirals of branches of flowers. Almost every time, the number that takes shape is somewhere along the Fibonacci line. We tidied up the lunar month and astronomical year and solved the problem of what to do with leftover spare time with the invention of the leap year. Our 24 hours are an accident. The Babylonians counted in 12s and worked it out with neatness rather than light or darkness.
It would be hard for an extraterrestrial life form not to have the concept of numbers. In fact, I think it's just plain impossible. The natural numbers are not an invention of mankind. They are a discovery. They existed. They exist quite independent of people. SETI has a single goal, to find evidence of extraterrestrial intelligence, presumably by receiving a beacon or message transmitted from another civilization. That's the jackpot.
Founded in 1995, Paul Horowitz's project at Harvard's Oak Ridge Observatory is the latest venture set up by SETI, the search for extraterrestrial intelligence. Their radio telescope is directed to the stars to listen into any messages that may be sent out from other planets.
We believe the best way to communicate over galactic distances is with radio waves, and in particular with microwaves, radio waves in the microwave region of the spectrum. Our experiment consists of using a radio telescope, which is simply a large directional radio antenna, to search for intentionally transmitted radio signals coming from space at those wavelengths that we believe are optimum for communication. That civilization couldn't build telescopes, couldn't build rocket ships, couldn't build radio transmitters if they couldn't build equations that predict and describe and indeed allow them to do this behavior. To form an oscillating current in a piece of wire, wiggling it 1,420,000,000 times per second, which is what you would have to do to transmit to our antenna in our experiment, requires more than concepts, more than non-mathematical language. It requires at some level the ability to predict what an electronic circuit will do, what an antenna will do, what the atmosphere will do, what space will do to a signal generated and transmitted in this way. And maybe it may not look like our mathematics, and they certainly don't call it mathematics, but that's the thing that seems required in any civilization that's going to participate in technological communications, or indeed any technology of this sort. What would the alternative be? That they basically manipulate pictures and somehow they'd arrive at a design and implement it? Hard to imagine. The question always comes up, what do we do if we find a signal? How would we communicate with creatures that may not even be biochemical or carbon-based, who come from a planet 100 light years away, who don't speak English for sure? And so there have been attempts to construct cosmic languages. You could go one bleep and then some symbol, and then one bleep and then some other symbol, and then two bleeps. It's likely that the first symbol is a plus and the second symbol is an equal in the way we think about integers and addition and equality. One could send little images, ones and zeros, be black and white spots, to be reconstructed into a raster, a two-dimensional image, by sending a stream of ones and zeros whose length is a product of two prime numbers, two approximately equal prime numbers, and the thing has a coherence. It shows carbon chemistry, it shows DNA, it shows creatures, it shows planets.
These numerical codes, translating into pictures, have been sent out to nearby star constellations by SETI scientists. For them, a universal ability to understand numbers is taken for granted.
Maybe we're just being provincial about this. We use math, so we think other people do. To me, it seems more basic than that. As Feynman says, it's more than the language, it's a whole method of deduction. The fact that you can write something in an equation is more than mere decoration of an idea that you had in your head. It implies a connection to other equations, to other predictions that follow from the mathematical coherence. If Earth continues to develop technologically at the rate we have, and to field experiments looking for these signals at a vigorous and healthy rate, then I would be surprised if, in another century, we haven't established contact.
I am Rettig, ruler of the moon. Apparently you are expecting me. Of course. For many years, our radio has kept us informed of events on Earth. And my men there have advised me of your every move. I see you have adopted our language. Yes. All our people are required to speak English, so we can operate more efficiently in your country. Mind telling me why your men are carrying out that campaign of destruction?
We have yet to wake up from Descartes' dream, 10th of November 1619, of a set of mathematical laws that could add up to a theory of everything, a net of infinite geometry that grows as it is thrown to catch matter as we find it. Descartes' promise, give me extension and motion, and I will construct the universe.
The answer to the great question, yes, of life, the universe, and everything, yes, is 42. It was a tough assignment.
42?
Some people are appalled by the vision of a universe governed by abstract, impersonal mathematical laws. I'm not entirely happy with it myself. I mean, a world governed by nymphs and dryads in many ways is preferable. But there's a process of growing up that we all do individually in our own lives. We learn there is no tooth fairy, there is no Santa Claus. Eventually we learn to stand on our own. And I think also our species is going through a process of growing up and learning that the laws of nature were not written with humankind in mind.
From its very beginnings, science has always been preoccupied by the quest to find the fundamental laws of nature. But it was the mathematics of the 17th century that turned this into a genuine possibility. Newton's laws of gravity and motion inspired a modern search to find a single theory of everything.
When Newton's theory, embodied in his great book, The Principia, was first developed, there was one big idea that spread all over the world and that changed everything. And that was that nature is governed by strict, impersonal mathematical laws. Even if people didn't understand the mathematics in which those laws were expressed, the idea of a universe governed by knowable, impersonal laws was tremendously important in our culture. I think it had a lot to do with changing the level of superstition with which ordinary people live their lives.
Like a complex watch mechanism, Newton's world was knowable. It would only take time before we fully understood it. This confidence was eroded in the 20th century, until quantum mechanics offered up a new hope of discovering a final theory.
The discovery of quantum mechanics, with its strange ideas about probabilities and wave functions, was a tremendous step away from the understandability of Newtonian mechanics, where particles just are moving around. And it's getting worse as time passes. In fact, the latest ideas are that time and space themselves are concepts that appear only on a certain approximate level, that at the deepest levels our theories are not going to be formulated as theories in space-time. So how are they going to be formulated? Well, they're going to be formulated mathematically in terms of mathematical structures that may already exist. There are things called conformal field theories that seem to play a central role in these new theories. In a way, this is tragic, because this language of mathematics that we find more and more indispensable makes a greater and greater gulf of understanding between what the scientist discovers and what the public has the language to understand.
What scientists mean today by a final theory is the goal of uniting the known fundamental forces of nature. It's a goal that has been brought closer by Steven Weinberg himself, who won the Nobel Prize for uniting electromagnetism with the weak nuclear force. But is the final theory really within our grasp?
I have no idea of what a final theory will look like. Our best guess right now is kind of theory called string theory, which for the first time offers the possibility of unifying our theory of gravitation with our theories of the other forces of nature. But whether the string theory is correct, we don't know, and whether, if correct, it will be the final answer, we don't know that either. And it would be premature to try to say what a final theory would look like. How will we know when we have it? Well, we already have a pretty good theory that describes most of what's seen in nature, called the Standard Model. It has some arbitrary features. It has about 18 numbers that have to be simply taken from experiment to make the theory work. If someone tomorrow publishes a paper, and perhaps a string theory, in which we can deduce the Standard Model as a logical consequence, and the 18 numbers turn out to be right, turn out to be what's measured experimentally, I would say then we would conclude that very likely is a final theory.
If and when a final theory is found, it will be written in the form of mathematical equations few, even in the scientific community, will be able to understand. But many believe that, like Newton's discoveries of gravity and motion, its impact will spread out to affect everyone's conception of the universe. Physicists are leading the search to find a final theory, but they depend upon mathematics as their guide.
I sometimes have the feeling when a branch of mathematics that I hadn't even known about turns out to be just what's needed for some application in physics, that, my God, they've been there before us again. And it's a little bit like the feeling that Neil Armstrong would have had when he landed on the moon, if he had seen in the lunar dust in front of him the footsteps of Jules Verne. Without mathematics, we're blind. We don't know what we're doing.
Whether numbers are an invention or a natural code we have yet to crack, we still put faith in them as facts. The world takes shape in numbers, giving us prediction, probability, scale, and symmetry. But as the mathematical map grows, it reveals unknown territory in which we move with as much instinct as authority, as much imagination as certainty.
There's a booklet celebrating numbers. For a copy, just send a cheque or postal order for £3.50, payable to Channel 4, to PO Box 4000, London W12 8UF. Well, next week's Equinox follows the unique work on head injuries by the world's most controversial neurosurgeon. Coma is on Monday at 9.